Hello, I'm Ginger Pan. Let me finish off the task I set for myself last time, which is to explain the finite element method in 30 minutes. Let me do that using a simple example of a solid bar, and the one end of this bar is fixed on this wall, another end you apply a force, and let's call that force P3 there. And if you apply a force there, and the material will deform, we have a bit of deformation, and you have that cross section will move to the right slightly. So we call that displacement, and that displacement, let's give it a name and call it U3. And let me identify another cross section which is in the middle of this bar, and similarly apply a load there. That cross section will move to the right slightly, and let me call that displacement U2. The idea of finite element method is actually quite simple. It's just to apply the Castellano theorem at the point where or at the cross section where I've just identified. Remember, the Castellano theorem relate a force to its corresponding displacement through the total strain energy. That's the idea of the Castellano theorem, which I explained last time. So if I apply Castellano theorem to this section here, so that's what I have. I have strain, if I differentiate total strain energy with respect to that displacement, the U3, I should get P3, right? And this U is the total strain energy of this structure. I can then apply that Castellano theorem again to this middle section there. So the strain energy U2 equal to P2. The idea is this gives us, because what do we want to find out are these U2 and U3. So I apply load, they move. So I want to find out how much that section has moved, the displacement U3, how much that section has moved. Yeah, that's what you want to solve. That's what you want to find out. And the way to find out that is to have these two equations, and they turn out to be a linear simultaneous equation for a linear problem. I'm going to demonstrate that to you in a minute. That gives me two equations, because I have two equations, I have two unknowns. If I solve them from this, then I can calculate from this displacement, I can calculate strain in each of this material. For material 1, the strain in material 1 is approximately that displacement divided by the length. The strain is change of length per unit length. Change of length per unit length level 2, so I can calculate strain. And I can also calculate strain for the second part of the material, which is that displacement minus that displacement. So that's change of length, divided by length, which is L over 2. I got the strain in this part of the material. Then I can calculate stress. Stress is Young's modulus times strain. So that's problem solved, because then that gives me, I can calculate the stress. So it's stress analysis. So I find displacement first, and then I find the strain. From strain, I use Hooke's law, I find out the stresses. So that's the logic flow of finite element analysis. It's actually very simple. But let me just demonstrate to you how to actually do this for this simple case. So what I need to do is to calculate this total strain energy. Once I've done that, problem is solved. I just follow the logic I've just explained. So to calculate total strain energy, let me just simplify the problem a little. So let's just consider a uniform bar. If I apply load P there, and its length is L, and it got a bit longer, so it changed length by a small length delta L there. So that force, you pull change length, it does work, so that becomes strain energy. So strain energy for that is simply 1/2 force divided by change of length, delta L, yeah, that's delta L there. So then let's just use the concept of strength and strings and manipulate this a little bit. So this is going to be 1/2. Force is stress times the cross-section area. Yeah, let's say this thing has a cross-section area, and that's A. Yeah, and change of length is string times L, time length of the bar. Right? And let me rearrange that. So that's going to be 1/2 stress times string, A times L. Yeah, I just shift this around. And then I can use Hooke's law, I got Hooke's law there. So this is Young's modulus times string, A times L, cross-section area times length, is the volume of this material. So this is volume. Yeah, this is the volume of material. So this will end up with 1/2 E string square times volume of the material. So this is how I can calculate the strain energy in terms of the string, yeah, Young's modulus and volume. So remember that. What I'm going to do next is I'm going to apply this to this situation here. Now we have an expression of string. Yeah, for this part of material we know string is that. For this part of material we know string is here, so I need to substitute these two strings in here. But what I need to do is I need to calculate this total strain energy one part by another. Yeah, so I calculate total strain energy for part 1, and then I calculate my strain energy by part 2, and the strain energy will be the addition, sum up of these two. Okay, so let me just do that. So U is going to be, so I'll apply that equation. So that will be 1/2 E, and for part 1 is going to be U2 L/2 square plus and times the volume of this material, so that's V1. And then let me get rid of that. Plus 1/2 E U3 minus U2 L/2 square V2. Right? So this is the total strain energy of this bar. Okay? So let me find myself some space. So now if I apply the Castellano theorem, so now I have a strain energy expression for the strain energy. So what I need to do is I need to do partial differentiation. I need to differentiate this whole thing with respect to U2 here. So there's a U2 there. There's a U2 there. So if I do the U2, yeah, and that gives me 4E L square U2 V1 minus, so the minus sign there, so 4E L square U3 minus U2 times V2. Right? It's a little bit messy. And that's the U2, and that has to be equal to P2. Right? And then I can do the second one here. So du3, but I don't have U3 here, I only have U3 there. So if I do, so let me just get rid of that. du3 equal to 0, and that gives me 4EL U3 minus U2 times V2 equals to P2. Okay? P3. And now I have two equations, yeah? You see, that's equation 1, that's equation 2. And we know Young's modulus, we know length, we know volume, we know the load we apply, P3. We know Young's modulus, we know length, we know V1, V2, E, we know everything else. The unknown, the thing we want to find out that U2 and U3 have two unknowns, we have two equations, we can solve them. I haven't said anything about P2. There's no P2. We didn't apply a P2 there. So P2 is actually 0. You can, because if you apply a P2 there, that's still fine. But in this special case, in this special example, this is actually 0. Yeah? But let's leave it there. Yeah? So that's it. Yeah? This is the equation, linear simultaneous equation we want to solve. What you can do in the finite element sort of terminology, you can write these two equations into a matrix form. Now, this is in a form of an equation. It's a bit messy, but if you write them in a matrix form, let me show you. Let me just write down that. If you write that in the matrix form, you have this. Yeah, the two equations I've just derived, I showed you before, you just need to reorganize them a little bit, and that you can write them into this matrix form. Basically, that means that times that equal to that, and that times that equals to that. Yeah, if you're familiar with the matrix expression. So that's the equation, and of course, you can solve these equations, and you solve these equations, you find strain, you find stress. And this is called the stiffness matrix in finite element method. This is called the vector of unknown or displacement matrix, and this is called the force matrix. Right? So that's it. That's the idea of finite element method. I want to finish off by telling you that by dividing this bar into two parts, and this is called element, I divide them into two elements, is not very accurate at all. Yeah? Because I've basically assume strain is a constant in each part of the material. Yeah? See, it's a constant. But it's not, because the stress is simply force divided by area, so stress changes is a continually change in each of the elements. Therefore, strain changes in each of the elements. So this is not a very good assumption. To make this calculation more accurate, what you need to do is to divide it into many small elements. And then each of them have a displacement, so ui plus n, un. Yeah? So you need to divide that by into a lot of elements. But it's not a problem, because then you can apply your Castellano theorem at anywhere you wish, at all these sections. So every time you add a new section, you add a new unknown, but you always have a new equation. So you always have enough equation. It's just this equation gets messy. Instead of just 2 unknown here, I may be 20 or so. So there will be 20 or so unknowns, and this matrix gets bigger. 20 times 20, and this false matrix gets bigger. Then you can't solve that equation by hand. You have to solve it using computer. And that's why finite element method only become powerful in the computer age. The equation you end up with, to solve a problem accurately, you have to use computer. Yeah? You have to use computer to solve the large simultaneous, linear simultaneous equation. But the fundamental idea is actually quite simple. Finite element come from the point that you have to divide your material into a lot of small elements. Thank you.